So from now on, we are recording the session. Okay.
Okay. Should we start, or should we still wait for people to trickle in?
So unfortunately, the last two sessions there was some problem with the recording of the sessions. I'm still trying to get it, but it seems it's not possible.
Okay.
Okay.
All right. Do you know if Adrian and Ariel will be joining? Should we wait for them?
I don't know if Adrian is coming, because Adrian actually is now around UK attending some meetings, and I think he was also visiting some university for his daughter. So I don't know if Adrian is attending. So
He's probably
maybe in 2 minutes we could try to start, I think.
Yeah, Euro is happening so in somewhere in the UK, and then next week is Europe, which I'm going to be going to. And so,
yeah. Let's see. Is there.
okay, maybe I can go ahead and start. All right. Speaking to that microphone, I've muted my computer's microphone to keep feedback. But welcome everyone to. I think Hanara, is this the last seminar?
Yes. This is the last seminar of this semester. We will restart again in the middle of September, I think.
Great. So, and it's nice. Qinyu Yang, my student, PhD student, he just joined me last semester. So in the winter semester of 2024-25, and he came to. I was lucky enough to get him to come to Göttingen after he finished his master's thesis at University of Bonn. And before that, he was a bachelor student at Mainz, University of Mainz. So, and he's made a lot of progress very quickly. And this talk will kind of close out where we started this semester with Rafael's talk about Wasserstein spaces. And Qinyu will tell us about optimality conditions in the Wasserstein space. So, can you take it away?
Oh, yes. Thank you for the introduction. And today, as our sixth talk in this seminar, which also the third talk on topic Wasserstein space, we have seen some basic geometric property and the Wasserstein space. And today, we're going one step further and consider the optimizations problem on the Wasserstein space and derive the first order optimality conditions for this kind of problem. So here is our motivation. Assume that we want to minimize some functional J defined on the Wasserstein space. Technically, the Wasserstein space have different kind of order. I mean, P can be equal to 1, 2, and any greater real numbers. But we will focus on the Wasserstein 2 space, and I will refer to the Wasserstein space as the Wasserstein 2 space, which means the measures with finite second order equipped with Wasserstein 2 distance. So minimize such a functional J defined on the Wasserstein space without constraints or with equality constraints given by K mu equals to 0, or even inequality constraints subject to a K mu smaller than or equal to 0. So our goal is to derive first order necessary and sufficient conditions for all three types of optimization problems. And here our challenges are following. Firstly, how to define the gradient of such a functional defined on the Wasserstein space, mapping from P2 to R. And consider about the Riemannian geometry. We're minimizing some functional defined on Riemannian manifold, and we derive the Riemannian gradient, and the gradient belongs to the tangent space. So naturally, we have to ask the question, what's the differential structure of the Wasserstein space, aka what's the definition for the tangent space and in tangent bundle? What's the local metric? And the third question is what's the necessary and sufficient conditions for this type of question? So with these three main questions in mind, here is our talk planned. The talk will divide into three parts corresponding to three questions we're going to talk about. Now, firstly, I have to pick up some basic definitions and basic properties of the Wasserstein space. Basically, what's the optimal transport problem, what's the Wasserstein distance, what's the interpolation, the geodesic, and do a little bit extension. I want to define the kind of convexity. Of course, the Wasserstein space is not a linear space, so it's useful to define a geodesical convexity. And in the second part of today's talk, I'm going to define the Wasserstein gradients and the tangent space. And I will give some examples for differentiable functionals defined on the Wasserstein space. And as the third part of today's talk, I want to state some optimality conditions. Good. And here are 5 main references I used. Firstly, today's talk is based on, or mainly based on, the paper from Nicolas Lazzenti and another 2 authors. The paper, First Order Conditions for Optimization in the Wasserstein Space. And for the basic geometric or properties of the Wasserstein space, I refer to the book An Imitation of Optimal Transport, Wasserstein Distance and Gradient Flows, and also the standard textbook from Cedric Villani, Optimal Transport, Old and New. As for the differential structure of the Wasserstein space, I would refer to the book Gradient Flows in Metric Spaces and in the Space of Probability Measures, as well as the paper on differentiabilities in the Wasserstein space and well-postedness for Hamilton-Jacobi equations. So here are 5 main references. I will record these 5 references at the very end of my talk. So, first part, let me give a quick review on the optimal transport problems. So given 2 measures, mu and nu, there are 2 Boolean measures or probability measures on RD. A vector field T from RD to RD, we said it transports mu to nu, in short T, a mu arrow nu. If nu is the push forward of T, this is the definition of push forward. It's basically the measure of the pre-image of A in T and take the measure, and that's the push forward. So if this equality holds, then we say that T transport mu to nu. And the Monge optimal transport problem seeks for the minimum of the Monge functional. It's an infimum over all such kind of transport maps. And the functional is defined as the integral on RD of the squared norm of x minus tx using the measure mu. And that's the Monge formulation. The infimum is taken over all these t's. And we will call any minimizer T star of the Monge functional and optimal map. And it is usually denoted by T with subscript mu and superscript nu to indicate that this is the optimal map, then push mu to nu. So now I would define the set of couplings using capital gamma. Gamma, mu, and nu. This is defined as the collection of probability measures on RD times RD, whose marginal distributions are mu and nu. The marginal, I mean the projector onto the first and the second argument, then push forward to this gamma, it gives us exactly the mu and nu. So this set is called a coupling. And Kontorovich optimal transport problems seeks for the infimum of the Kontorovich functional in K gamma. This infimum is taken over all couplings of mu and nu, and the Kontorovich functional is the integral on RD times RD of the squared norm of x minus y using gamma. And I will denote by gamma star as the optimal couplings or optimal planes. They are the argmin of the Kontorovich functional. So here are Monge for optimal transport and Kontorovich optimal transport problem. The Wasserstein 2 space, in this talk, I will just call it the Wasserstein space. The P2 is defined as those probability measures whose second moment is finite. And the Wasserstein distance is the square root of the minimum of the solution, aka the minimum value of the Kontorovich problem. So this is the Wasserstein distance. And the celebrated theorem from Brenil tells us, so given mu and nu, two measures in the Wasserstein space, and assume that, I use in red, the mu is absolutely continuous with respect to the d-dimensional Lebesgue measure, then there exists exactly one unique optimal plane gamma induced by one unique optimal map. I mean, the gamma is the push forward on mu, push forward of ID identity and this optimal map. And this optimal map, this T, this is given by the gradient of some convex function. So I want to emphasize two points. Firstly, this mu is absolutely continuous with respect to the d-dimensional Lebesgue measure. And here for RD, this is equivalent to existence of a density function. And this psi function, and this is a convex function, and its gradient is the optimal map, this T. So yeah. And we will see that the power of absolute continuity. So this will give us a unique geodesic space. And this theorem actually motivates to define the following set. The P2AC, AC stands for absolutely continuous. The P2AC is those measures in P2 with absolutely continuous to LD. So this set, again, equipped with the Wasserstein distance, is a uniquely geodesic space, and it stands in W2 sense. In W2 sense, meaning it's the dense in with respect to the topology measured by the W2 measure distance. Sorry. And it's uniquely geodesic, meaning that each 2 points in this set is connected by a unique geodesic, and the whole curve is also contained in the P2AC. So any intermediate point on this geodesic curve is again absolutely continuous. That's the power of this absolute continuity. This actually is connected to a so-called Monge Ampère equation, but I won't go into details at this point. Good. And now we have two kinds of convergence. The narrow convergence. This is tested with or continuous but bounded function on RD. So a mu k converges to mu if I integral this this function f with mu k. This value converges to the integral of f using mu. Another convergence is called weak convergence. In addition to the narrow convergence, I also require that the second moment convergence, the moment of mu k converges to mu. And this is used this arrow, mu k converges mu. This weak convergence is somehow more important in today's talk because it is measured by the W2 distance. While the narrow convergence, it is measured by the Levy-Prokhorov distance. Yeah. So this lemma, I think, is something new today. It's called perturbation of probability measures. So given some measure in P2 and given some psi, a CC infinity function on RD, then there exists some S bar greater than 0, such that the ID plus this S times gradient of the psi is an optimal transport map from mu to the ID plus S gradient and push forward to mu for all S defined in this interval. That is, recall this notation. This means this is the optimal map from mu to this map. This map is from mu to this measure. This is ID plus S gradient push forward mu. And yeah, furthermore, the ID plus S gradient push forward mu is again an element or a measure in the Wasserstein space. And we have a very nice formula to calculate the distance between these two measures. It's given by the absolute value of S times the L2 norm of this gradient. So this perturbation lemma actually allows us assume that we have some P2 measure. So give a small perturbation S, and SS can be something small real number. And after that, we still get a P2 measure, and we know how much we change. It's given by the S, the step size, and times the L2 norm of this gradient. This is very useful in the numerical algorithms, such as gradient descent algorithm on the Wasserstein space.
Question.
Yes.
So I'm still astonished by the fact that you had on one of these previous slides that the Xi function, whose gradient is the optimal map, the transport map,
Yes, exactly.
is convex.
Yeah.
Which means that the gradient is monotone. So this is just saying that the optimal transport map, when you're in the space of absolutely continuous functions, when you restrict to absolutely continuous measures,
Yes.
the optimal transport maps are monotone mappings.
Actually, we don't quite use the monotonicity. The Lipschitz continuity is more used because the gradient.
Okay, so there's an equivalence then between monotonicity and Lipschitz continuity. Okay, so if you go forward, because this perturbation result doesn't anywhere refer to convexity of Xi. Xi is just some C infinity.
Actually, in this theorem, no, because this mu is not necessary to be absolutely continuous. And we also do not state that this is the unique optimal map.
Okay.
Yeah.
Okay.
This limit is just telling us if we have some P2 measure and give a small perturbation, which is a gradient of some CC infinity function, then we can still be a P2 measure. And the distance is measured by the absolutity as the step size times the L2 distance.
Okay.
Yeah. Good. Yes. We have talking about, or we have used the name the geodesic curves. So given two measures, mu0 and mu1, and some gamma in the set of optimal coupling, then we define this as the Macron's interpolation. This is 1 minus t projection to a first argument plus t times the second argument and push forward to gamma. This kind of curve is called Macron's interpolation. And the curve defined by Macron's interpolation actually defines a constant speed geodesic in P2, which means it satisfies, we have S and T, there are 2 times points between 0 and 1, and this distance is T minus S times the whole distance from mu0 to mu1. So this is the geodesic. Actually, if we are in an absolutely continuous case, then all geodesic curves are given by this form, by this Macron's interpolation. Yeah. So with geodesic curves defined, we can define the geodesical convexity. So a functional now J from P2 to R bar, I use this to denote the extended real numbers. This is defined as R union with the positive infinity. This kind of functional is called alpha geodesically convex, with this alpha belongs to R. If for all mu0 and mu1 P2, The J mu t is Macron's interpolation, some intermediate point on this geodesic curve. The functional value at this intermediate point is smaller than or equal to 1 minus t times J mu 0 plus t times J mu 1 minus this additional term, this minus alpha divided by 2 times t times 1 minus t times W2 distance between mu 0 and mu 1 s squared for all t belongs to 0 and 1. So what's the difference between this definition and the convex functional we usually use in a general metric space is here, the additional term. So this additional terms with this alpha allowed to be all real numbers. And this gives us a lot of degree of freedom. If alpha equals to 0, then we recover the original definition for convex function. And if alpha is greater than 0, it will give us at least a quadratic growth in some kind of sense. Yes, this is very powerful tool to analyze the optimality condition, especially in the sufficient condition. Because in the Euclidean setting, the first order sufficient condition would be convexity plus greater than or equals to 0, or 0 belongs to subgradient. Yeah, so this is totally analog in the Wasserstein space, where it requires alpha geodesic convex. And in today's talk, I also use the terminology alpha convex. For a real valued function, f from Rd to R is called alpha convex with alpha in R if alpha x minus alpha times square norm of x is convex. So as a footnote here, is this alpha convex? I will use it in some examples. Good. Now here are some basic geometry property of the Wasserstein space. Now we can define the gradient. Good. Given some mu, we denote by L2 mu as the squared integrable vector fields with respect to the measure mu. This is the Hilbert space and equipped with the scalar products f and g. I use the subscript mu to indicate this kind of scalar products, and this as well as the induced norm, the norm of f with subscript mu. This is the square root of integral of this square norm in Rd of fx and integrating mu. Good. And here is the definition for Wasserstein sub and super differentials. This is the first and very important definition in today's talk. So given some functional j from P2 to extended reals, so let mu be measured in the domain of j. In domain or effective domain of j is those measures where j is smaller than positive infinity. And we say that a function in L2 mu, recall that L2 mu is the Hilbert space, squared integrable vector field. So a function psi in L2 mu belongs to the subdifferential of j at mu if the j nu minus j mu is greater than supremum over all gamma in the optimal coupling set. This integral, the scalar product between psi x, y minus x, and integral this quantity of this function using gamma. And we have a reminder, the higher order term of the distance between mu and nu, and for all nu in P2. And in this case, we see that psi is a Wasserstein subgradient of j at mu. This is an analog in Euclidean setting. In Euclidean setting, we do not have this soup, we do not have this integral, we just have this scalar product, psi and y minus x. So intuitively, the subgradients or subdifferential is the experience or expectation of the particles near x. That's why we have this soup of gamma star of this gradient. And we also use this to define the superdifferential. Similarly, the psi belongs to the superdifferential partial plus of j at mu if the minus psi is the subdifferential of minus j at mu. Explicitly, it fulfills such kind of inequality. I replace this greater than equal to smaller than equal and replace sup by inf. And in this case, we see that psi is a Wasserstein superdifferential of j at mu. Yeah, good. So Then the Wasserstein differential is defined as the intersection of the subdifferential and the superdifferential. So a function of JA is called is Wasserstein differentiable at mu in the domain if the intersection is non-empty. And any function in this intersection is called the Wasserstein gradient of J at mu, satisfying the following equality. This is basically just, you see, it's greater than or equal to the supremum and smaller than or equal to the infimum, so we get the inequality here. For any mu, nu in the Wasserstein space and gamma is in the set of optimal couplings. Good. And so a natural question would be, is this Wasserstein gradient a unique element? In general, no. This set can contain more than one element, but the Wasserstein gradient is unique up to some equivalent relation. We'll see this. Before point out this point, I have to first define the tangent space. So the tangent space at mu to the Wasserstein space is the vector space. The tangent mu as a Wasserstein space. It's the gradient of function of CC infinity functions, and we take the closure in the topology of L2 mu and equipped with the local metric, the scalar product with mu. Recall that this is defined as the scalar product in RD and integral with measure mu. So it's the gradient of CC infinity function and take the closure. In closure, what was the topology here? The topology is the L2 mu topology here, equipped with this local metric. So with this tangent space defined, we may ask, okay, well, we have a tangent space, we have a tangent bundle. Is Wasserstein space a Riemannian manifold? Actually, no, definitely no. Because whether a space or set in this kind of structure is a Riemannian manifold, this depends on a quantity called injectivity radius. So if it's a Riemannian manifold, then the injectivity radius should be something, I think it's strictly greater than 0. It can be shown that the injectivity radius in this kind is exactly 0, which means it's not a Riemannian manifold. So yes, it's not a Riemannian manifold, but why it's important here, so being a Riemannian manifold or not? The answer to this question is, it depends on the motivation of how we define the smoothness or how we define the tangent space. In Riemannian geometry, the smoothness is defined by a charge and atlas. And for the embedded submanifold, it's defined in RD sense. Yeah. But for the Wasserstein space, we do not have a charge. We do not have atlas. We do not have an atlas topology. Yeah. Topology is given by the Wasserstein distance. But still, we can define this, formally define this tangent space. So in some reference, in some literatures, we usually call this the pseudo-Riemannian structure to emphasize this point, that the Wasserstein space is not a Riemannian manifold. Another huge difference is a Riemannian manifold, whenever it's finite or infinite dimensional, it's locally flat. Because in the sense of diffeomorphism, it's a diffeomorph to RD or some Hilbert space. But for Wasserstein space, it's not the case, unfortunately. We shall see this effect. So anyway, we have defined the tangent space here. Why we can say that the Wasserstein gradient is unique is that's due to the Hilbert decomposition theorem. So note that this function xi belongs to the L2 mu here, the L2 mu. And the tangent space at mu is actually a closed linear subspace of this Hilbert space. So due to the Hilbert decomposition theorem, it can be uniquely decomposed into two parts. The xi can be written as xi parallel plus xi perpendicular, with this xi parallel belongs to the tangent space. It aligns with the direction of this tangent space. And another part is xi perpendicular belongs to the perpendicular, or we call it orthogonal complement of the tangent space. Sometimes this space is also called normal space.
How do you define orthogonality?
Oh, we have the L2 mu scalar product.
Okay.
So yes.
Okay.
In
the normal, in the sense of
yes, exactly. The tangent space is equipped with exactly the same metric as the L2 mu space. So we can define the orthogonality. We use this metric. Totally analog to the Euclidean case.
Okay.
Scalar product equals to 0, which means perpendicular. Yeah. This composition can be viewed as an orthogonal projector onto a subspace, a convex and closed sublinear subspace. So this guarantees the uniqueness of this psi parallel. And it can be shown that this part, the part that is perpendicular to the tangent space, x has 0 act on this x minus y integral. Yeah, here. So y minus x, x minus y, no difference, just a sign difference. It can be shown that this integral is 0. So if a modular or build a quotient, modular this normal space, we project every vector in L2 mu onto the tangent space. Then the Wasserstein gradient is unique in this sense. In particular, the Wasserstein gradient of J at mu is a unique element. I use the notation nabla W2. Nabla subscript W2 means that it's the gradient taken in the Wasserstein sense, belongs to the tangent space in mu, intersect with the subdifferential, intersect with the superdifferential at this point. Good. So now here we have defined the differential, subdifferential, superdifferential, and tangent space. And we know that if the Wasserstein gradient exists, then it's unique in the sense of modulo the normal. Then it's natural to see the calculus of this kind of differentiability. And let's first see some properties. Firstly, as in Euclidean sense, and differentiability is stronger than continuity. It can be shown that if a functional J is Wasserstein differentiable at a mu measure here, then J is also continuous at this point. J is continuous with respect to the weak convergence in P2 at mu, aka with respect to the topology measured by the Wasserstein distance. The convergence, the differentiability is stronger than continuity. Now we have the sum rule and multiplication rule. So now let J1 and J2 be two functionals defined on the Wasserstein space who are subdifferentiable at some point mu. Then the subdifferential of the sum is a superset of the sum of subdifferentials. And if alpha is a non-negative constant, non-negative real, then the subdifferential of alpha times J1 is the alpha times the subdifferential. So why we have this inclusion, not strictly equality, and why we restrict ourselves to non-negative reals, the reason is that they're just subdifferential. For subdifferentiable, we have an inequality. So we want to preserve the sign of this inequality, direction of this inequality. So we just have the multiplication rule with non-negative constant. And now, in particular, if J1, one of them is differentiable, then the subdifferential is exactly the Wasserstein gradient plus the subdifferential of another functional. It's quite easy to understand this point because the Wasserstein gradient is unique. It's a unique element in the common intersection we seen in last theorem. So the subdifferential of this J1 is some kind of unique things determined, and it only reminds the subdifferential of J2. And now we have equality because we are differentiable, not just the subdifferentiable. We have differentiable here, differentiability. We have equality. So in differentiability case, we allow this alpha to be all real numbers. And that's the sum and the multiplication rules. And we have the chain rules. Let G be some real function from R to R be differentiable, and let J be Wasserstein differentiable. Then the composition of J of this G and J, again a mapping or a functional from P2 to R is again Wasserstein differentiable. And the Wasserstein gradient is, as we expect, the gradient of J of G at the point J mu times the Wasserstein gradient. And it is well defined because G prime as the J mu is just some real number. And the Wasserstein gradient is an element in L2 space. So it's well defined. That's a chain rule. Now we have defined the differentiability, and we have seen the property of this differential. Now it's time to see some examples. Sorry, again, we're still not finished with the property. A large problem is how to overcome the curvature. So the remedy would be the geodesic convexity. I will recall the curvature the property in later. So what's the gradient of a convex function? This is very useful property to show the sufficiency of the first order condition. That J be some alpha geodesically convex function, functional at mu with some constant alpha. Suppose that J is Wasserstein subdifferentiable, and let Xi be any subgradient. Then for all nu, the J nu minus J mu is greater than or equal to the supremum of this integral. This integral comes from the subdifferential. Now we know what's the Riemann term. Now, in the original definition of subdifferential, we have just a higher order term. And if the functional is alpha geodesically convex, we know what's the explicit form for this higher order term. It's given by alpha divided by 2 times the squared distance between mu and nu. This is a very powerful tool or very powerful property for convex functional because it allows us to have a quadratic growth here. That's it, a plus growth. It's differentiable at mu, so the difference will get some growth in this term. It's positive. Let's see the proof, but just a sketch. So now let gamma be an optimal coupling. And the geodesic convexity of J allows us to rewrite the inequality in this form for t belongs to 0 and 1. Mu t is an intermediate point on the geodesic curve. So recall that the original definition is J of mu t is smaller than or equal to 1 minus t, J mu plus t, something like that. So this is just a reformulation, but t is greater than 0. And it can be shown that gamma t defined in this form is still optimal. It's an optimal between mu and mu t. Mu t is an intermediate point. It's defined as projection to the first argument, and 1 minus t projection on the first argument plus t times projection onto the second argument and push forward to gamma. Gamma is an optimal coupling between mu and nu. So the gamma t defined in this form is optimal between mu and intermediate point mu t. I skipped the proof for this statement, but actually not so complicated. Then this is what we want to bound J nu minus J mu minus alpha divided by 2 by squared of the distance. The trick is we have alpha divided by 2 here, but we can add or multiply with 1 minus t, but take the lim inf for t goes to 0 from above. That's the first trick here. With this lim inf, we recover a similar formulation for the alpha convexity. Alpha geodesic convexity allows us to write an inequality is lim inf of J mu t minus J mu divided by t. That's why we intersect some 1 minus t here. And this, again, we have derived that the psi is the subdifferential. So this is the definition of subdifferential, of subgradient of psi, using gamma t. Gamma t is the optimal coupling between mu and mu t. And this step is literally the definition of gamma t. This allows us to get 1t outside this integral and cancels. And this is a higher order term of t that goes to 0 as t goes to 0. So the only remains the integral of psi x times y minus x and integral with gamma. And this is exactly the inequality we want to show. So this inequality holds for any gamma. Oh, that's why we can write a soup here. Yeah, this is a very powerful property. Yeah, now we can see some examples. The first important example is so-called the potential energy functional. Now let capital V be some twice continuous differentiable functional on Rd, C2Rd, with uniformly bounded Hessian. That is, the Hessian of V and its this norm is bounded by some capital M for all x in Rd for some constant m greater than 0. And we consider the functional J. This J is defined as the expectation of this energy functional V with using the measure mu, the integral on Rd of this Vx with mu. So this kind of functional, we intuitively, it has a linear dependence on this mu, because actually not regularly the linear, because we are not in a linear space. But if mu is in the whole P of Rd, it's some kind of linearity here. So it gives us some feeling that this is a linear dependence on this mu. And the gradient should be something independent on this mu, and it's exactly the case. So the functional defined like this, it's proper. The whole domain, its effective domain is the whole P2. That's because the C2 is bounded. And J mu is greater than minus infinity, of course. And J is continuous with respect to the weak topology, which means the weak in the W2 topology. And it is alpha convex along any interpolation curve if and only if V is alpha convex. You call that V is alpha convex, means that Vx minus alpha times norm of x squared is convex function. And J is Wasserstein differentiable. Its Wasserstein gradient is exactly the gradient of V in Euclidean setting. Yeah, the Wasserstein gradient of J mu at any mu is the gradient of V in Euclidean sense. So no dependence on this mu. Is what we expected. So it's the first important example. And the second important example is so-called squared Wasserstein distance. So fix some nu in P2. Consider the functional J mu is defined as 1/2 times the squared distance between mu and nu. This kind of functional usually occurs in such as the barycenter problem or in Fischer-Min problem given some different nu, and we want to minimize the squared distance to all nu's. So again, J is proper. Its effective domain is whole P2, and J is continuous. The Wasserstein gradient is the identity minus any optimal map between mu and nu, where the T is the optimal transport map from mu and nu. So why I write is unique here, because if we restrict ourselves to absolutely continuous curve, then it's again unique. So this is the Wasserstein gradient of this functional. And note that this functional J here is -1 concave along any interpolation curve. And this makes the Wasserstein space a positively curved metric space. So a positively curved metric space, we have no uniform convexity for this distance functional. And this fact will essentially complicate the analysis for sufficient condition, which is usually connected to the convexity. But as I said, the remedy would be the alpha geodesic convex, allows some additional term. And again, we have a quadratic growth. Yes. Good. Now we have seen some examples for Wasserstein gradient. We can see the optimality system, I think. Yeah, let's first consider the unconstrained optimization. So as we seek of the minimum of some functional J defined on the Wasserstein space, and we first define the local, global, and the strict minimizer. And just as in the Euclidean setting, a measure mu star is called a local minimizer of J if it is optimal in a small neighbor of mu star, which means there exists some R greater than 0, such that J nu is greater than or equal to the functional value of mu star for any nu in this open bore centered at mu star with radius R. So that's the definition of a local minimizer. For global minimizer, we just allow this R to be arbitrarily big, arbitrarily large. A measure mu star is called a global minimizer of mu of J if J nu is greater than or equal to the J of mu star for all nu in the Wasserstein space. And a measure mu star is called a strict minimizer, or we can call it the strict minimizer of J if J nu is strictly greater than J of mu star for any nu in the Wasserstein space which is non-equal to the mu star. Totally analog to Euclidean setting and the definition of minimizers. So the first of the necessary condition for unconstrained problems is following: that mu star be a local minimizer of J, just a local minimizer, and assume that J is Wasserstein differentiable at mu star. Then the Wasserstein gradient vanishes. So the gradient equals to 0 in the L2 sense. Why I have to emphasize in the L2 sense? Because actually it means that the Wasserstein gradient of J at this mu star, which is literally some vector field in L2 mu star. So this function or this vector field equals to 0, which means that it's 0 for mu star almost all x. We will see an example at the very end of this talk. So just keep in mind, any inequality in the L2 space is just the mu star or mu almost everywhere, or mu almost surely. It's not everywhere equals to 0. It's just almost everywhere equals to 0 in this sense, and in the sense of the corresponding measure here. And here is the proof sketch. Firstly, let T equals to the gradient of some psi, and psi is any CC infinity function of Rd. So psi is any CC infinitely differentiable function in Rd, which means T is again CC infinity function from Rd to Rd, and that's the test function we will use. Let epsilon be some small, and we allow epsilon to be positive or negative. So I will write for epsilon absolute value small. Let mu be defined as some kind of perturbation of this mu star. And we have seen that the Wasserstein distance between mu star and mu is measured by the absolute value of this epsilon times the norm of T using the mu star, or the norm of T in L2 mu star space. So this is the perturbation we have seen, the lemma perturbation. Yeah. Mu defined as perturbation for mu star. Yes, then mu star is the local minimizer, where the J is Wasserstein differentiable. Yeah. So the local minimality of mu star says that the J mu minus J mu star must be non-negative. And for epsilon greater than 0, the differentiability allows us to show the following inequality. Again, I skipped some steps in this inequality, but just literally plug in the definition of the Wasserstein differentiability. It's not hard to see here. Why we can cancel 1 times of epsilon here, that's because we have this perturbation formula, and that's the definition of this mu. Good. And this is negative because mu star is a local minimizer. Again, I skipped some steps here, but yeah. Then from epsilon goes to 0, we have this integral, basically the mu star scalar product in the scalar product of L2 mu star of the Wasserstein gradient and this T function. This is non-negative, greater than or equal to 0. And similarly, for epsilon smaller than 0, if epsilon is smaller than 0, we cancel 1 epsilon, but we preserve some minus here. We provide some minus here because the distance we cancel actually the positive of epsilon. And we have epsilon here, so we cancel leaving -1. So for epsilon minus smaller than 0, this function or this value again is smaller than or equal to 0, which means actually 0. So this means the Wasserstein gradient of J at mu and tested with T using mu star is 0 for any T grid equals to the gradient of this psi. Yeah. Which shows that this gradient. I think I am missing some star here. Because it's the scalar product of the Wasserstein gradient at mu star, actually. Mu star and tested with any CC infinity vector field. Yeah, it's 0. So it's 0 in the weak sense, aka it's almost everywhere. Mu star almost everywhere 0. Yeah, that's why here missing a star. That's the proof sketch for the first order necessary condition. Then what's the sufficient condition? Now, assume that J is alpha geodesically convex with some constant greater than or equal to 0. Then let mu star be such that J is Wasserstein subdifferentiable at mu star and 0 belongs to the subdifferential. Then mu star is a global minimizer of J. If additionally alpha is strictly greater than 0, then mu star is even the strict minimizer of J. The proof is following. The alpha geodesic convexity of this J yields the following inequality. We have seen the proof for this inequality. This is the proposition or the property for the Wasserstein gradient for the Wasserstein gradient for the alpha convex functional. Yeah, we have a quadratic growth term here provided by the alpha geodesic convexity, geodesical convexity. Since 0 belongs to the subdifferential, plug in, we get the J nu minus J mu star is greater than alpha divided by 2 times the squared distance from mu star to nu for any nu here. That means mu star is a global minimizer of J. Now, the whole right-hand side is controlled by this alpha. So if alpha is strictly greater than 0, then the inequality is strict whenever nu is non-equal to mu star. That's why it's the strict minimizer of J. So let me summarize a little bit. We have seen that the Wasserstein space is positively curved, and it will complicate the analysis for the sufficient condition, especially for sufficient condition for constraint optimization. And if J is convex, alpha geodesically convex with some additional term, we can show this part. Yeah. So that's the first order optimality condition for unconstrained problems. Now we want to add some constraint. We first consider the optimality condition for constraint optimization, where the constraint set C is given by some equality constraint. So minimize the functional J where mu is searched in C. C is given by K of mu equals to 0, and we call this problem P equal. The definition for local global strict minimizer is totally analog. We restrict ourselves to the C. So mu star is a local minimizer if it's minimal, if it's a minimizer in the small ball around mu star intersected with this C. And it's a global minimizer for this problem if it's a minimizer in C, and the strict minimizer if the inequality is strict whenever nu is feasible but not equal to mu star. So totally analog. We just add some additional constraint here. In order to derive or actually to state the first order necessary as well as the sufficient condition, we need to define the so-called continuous differentiability. Continuous differentiability. A functional K from Wasserstein space to R is called Wasserstein continuously differentiable at some point mu. If T1 is given by the gradient of phi1, T2 is the gradient of phi2, with phi1, phi2 are CC infinity functions, and there exists some epsilon bar greater than 0, such that firstly, K is Wasserstein differentiable at the mu defined as following. Now, we do not perturbate in one direction, we perturbate in two different directions, but we control our step size to be small. which means the epsilon 1, epsilon 2, but they belong to the interval minus epsilon bar and plus epsilon bar. Epsilon bar is a small positive real. So we perturbate this mu in two different directions, and we do not change too much intuitively. Second, the real value function. We view epsilon 1, epsilon 2 as some element from called R2, R times R, whatever. Basically, it's the second product of this interval. And we map it into this scalar product. We do not change too much. So the real value function given by this form with mu I equals to 1 and 2 is continuous for all mu epsilon 1, epsilon 2 in this interval. So this is called Wasserstein continuously differentiable. So the first of all, the necessary condition for equality constraint optimization would be let mu star be a local minimizer of P equal. P equal is the problem with equality constraint. Assume that firstly, J is Wasserstein differentiable at mu star, K is continuously differentiable with mu star, and the gradient of this constraint at mu star n equals to 0. Then there exists a unique multiplier lambda belongs to R, such that this equality holds. Again, this equality holds in the sense of mu2 almost everywhere, which means the gradient of J at mu star x plus lambda times the gradient of K mu star x equals to 0 for mu star almost all x in RD. Yeah.
Where's this? Okay, so there exists, and that's your Lagrange multiplier.
Yes, exactly. It's some kind of Lagrange framework.
When you get to the inequality constraint, this gradient of K is going to, you get a negative, and that's going to turn into the negative by some normal count.
Currently, we have just equality constraint.
Right.
Equality constraint. So yes, it has some connection with normal counts, but we do not define normal count in a Wasserstein space because it's non-linear space. Yeah. So it's kind of adaptation of this kind of framework. Yeah. And for first order sufficient condition, we require this J to be geodesically convex, and K should also be geodesically convex and concave. So why it's so complicated here is that's because it's positively curved. So if K, this inequality constraint function K, is both geodesically convex and geodesically concave, it gives us some taste that is some kind of linear function. We only state the sufficient condition for those kind of function. This difficulty is due to its positive curve. Suppose that there exists some lambda in R and mu star such that firstly, J is self-differentiable at mu star, K is differentiable at mu star. Mu star is feasible, and there exists some subgradient of J such that psi plus lambda times the gradient of K equals to 0. Then mu star is a local minimizer of P equal. Moreover, if J is alpha J geodesically convex with alpha J strictly greater than 0, then mu star is the strict minimizer of J on C. Yeah, if we compare this whole theorem with the usual Lagrange multiplying methods for Euclidean optimization, I think the most difference would be the requirement of this K, I would say. It's very restrictive.
Yeah. I mean, and it just gets, you have to ask the question, does such a K exist in any non-trivial?
Exists in the trivial setting. The author didn't give us some example of this kind of equality.
Yeah.
Yeah, good. And that's all for the equality constraints. As for the inequality constraint, now we allow the C given by some inequality constraint, K mu smaller than or equals to 0. I denote this problem with P smaller than or equals to 0. So the necessary condition would be let mu star be a local minimizer of P smaller than equal. Assume that firstly J is Wasserstein differentiable at mu star, K is continuously Wasserstein differentiable, continuous differentiable as mu star. And the gradient of this K at this point is not vanishes. Then there exists a unique multiplier, lambda, non-negative, such that the following system holds. This is some kind of complementary slackness condition. So if the constraint is active, then lambda should be 0. If it's not inactive, then it should be any non-negative real, because K mu star is a mu star is feasible, right? Means mu star is feasible. So K of mu star is smaller than or equals to 0. Now we require it to be 0. So lambda must satisfy the complementary slackness condition. And the gradient of J plus lambda times the gradient of K is equals to 0. And again, this gradient of this K mu star is non-vanish at this point. That's the first order condition for necessary condition. As for the first order sufficient condition, it's way large theorem. So let J and K are two functional defined on Wasserstein space. They are both geodesically convex. And suppose that there exists some lambda greater than 0 and mu star belongs to Wasserstein space, such that J is subdifferentiable, K is differentiable, mu star is feasible, and complementary slackness holds such that lambda times K mu star equals to 0. There exists some subgradient psi in the subgradient of J at point mu star such that psi plus lambda times the gradient of K is 0. Then mu star is a global minimizer of our problem. Moreover, if J is alpha J convex, K is alpha K convex, and the alpha J plus lambda times alpha K is greater than 0, then mu star is the strict minimizer. That will be the first order sufficient condition for being a local, for being a global strict minimizer of our problem. Yes, and here I have already two remarks. Since the Wasserstein space is positively curved and the distance function is not convex, unfortunately not convex, unlike the Euclidean setting, any constraint K involving the distance function, such as we require K mu, such as 1/2 of the distance to a certain mu is minus r smaller than 0, or the K mu of the distance is smaller than or equal to r. So any constraint, ever inequality or inequality constraint involving the Wasserstein distance, it will never fit in the sufficient condition we have derived here. That will be the terrible bad news here, because I would say the most common constraint would be well restricted to some ball, some kind of things, or some box, which means given by a certain some kind of distance constraint like this. But unfortunately, any constraint involving the distance will never fit in our sufficient condition. A remedy is here is given in the paper in our reference, the theorem 3.13. In this theorem, in particular in this theorem, the constraint given by the transport discrepancy is examined, and the authors gave us some system or the optimality system for such kind of constraint. But the whole framework is very complicated, and I think I don't want to introduce this kind of theorem here right now. For anyone who is interested in this kind of framework, I refer to the theorem 3.13 in the first reference. Yeah, good. Now let's see some example. Yeah, a very simple example, windy example. So consider the problem. We want to minimize the functional J, and the functional is given as the expectation. Recall that we have seen this, the expectation functional for energy functional, and the integrand is 1/2 times x squared. Now we are on P2 of r, d equals 1. So very simple example. It's just expectation integral this function with respect to the mu measure. The constraint is inequality constraint. One minus the expectation of x is smaller than or equals to 0. So simple functional and simple constraint. Basically, it requires that the expectation of x is greater than or equal to 1. And we know that the Wasserstein gradient of this expectation functional is given by exactly the Euclidean gradient of this function. So the gradient of 1/2 x squared is x, simple. And we have sum rule and multiplication rule for this k functional. And again, the Wasserstein gradient for this k is minus of the Wasserstein gradient of expectation is -1, some constant. According to our theorem for this inequality constraint optimization problem, the first order necessary conditions would be for lambda greater than or equals to 0, the x minus lambda, which means the gradient of j plus lambda times the gradient of k equals to 0, mu star almost everywhere. And the complementary slackness condition and some kind of lambda times 1 minus k, 1 minus the integral. This is exactly the k. So lambda times k equals to 0. Simple, no? The system, the gradient of j plus lambda times the gradient of k equals to 0, and the complementary slackness condition holds. So what does it mean? Clearly, the x equals to lambda, mu star almost everywhere. The x, y equals to x is just the diagonal line for in R2. I mean, this function should equals to some constant lambda, mu star almost everywhere, which means for x non-equal to lambda, the whole real line except lambda should have measure 0. So apparently this mu star should be the direct measure at lambda. For some lambda greater than 0, why we exclude the case that it's smaller than or equals to 0? Firstly, we require this lambda to be non-negative, so lambda can only be greater than or equal to 0. So why lambda is not 0? Because the delta measure delta 0 is not feasible. Plug in, mu is delta 0, so the function evaluation at 0, so this is just 0. 1 minus 0 is 1. It's greater than 0. It's not smaller than or equal to 0. So direct measure at 0 is not feasible. So after this kind of analysis, the only choice for mu star would be the direct measure for lambda strictly greater than 0, to fulfill this kind of equality system. And for the complementary slackness condition, so lambda times k is 1 minus integral using mu. Now mu is delta k, delta lambda. So this is 0, which means lambda times 1 minus lambda. This is integral with respect to the direct measure. It's just a function evaluation at this point. So lambda times 1 minus lambda equals to 0. It's a polynomial with 2 roots. Lambda equals to 0. We have excluded this case. So the only possibility is mu star equals to delta 1. So direct measure concentrate at x equals to 1 is the only choice for this mu star to satisfy the necessary condition. So do we have a sufficiency for this delta 1? Answer is yes. J and k, they are convex along geodesics because 1/2 x squared is a parallel. It's convex. And x, linear function, is convex. So so they're convex, alpha convex in the sense alpha convex. Alpha j is 1/2, alpha k is 0. So which means the mu star should be delta 1. And that's the only choice, and that's the strict minimizer, which means this constraint optimal minimization problem have exactly one strict minimizer at delta 1, because it fulfills both the sufficient condition and the necessary condition, and it's the strict minimizer because they are the constant here, they are positive and lambda is non-negative, and that's why we have the strict minimizer. So the analysis is not so simple here, I would say. And yes, I think I should stop here and let's do a small summary. We have seen in this talk, we first defined the tangent space as mu. The tangent space is the closure of the gradient of cis infinity functions using the L2 mu topology. And know that the whole Wasserstein space is not a Riemannian manifold, even though we can define the tangent space and the local metric, aka we can define the metric tensor, but it's still not a Riemannian manifold. That's important. And we define the Wasserstein gradient. It's the unique element in the tangent space satisfying this equality here. And for unconstrained optimization problem, the necessary condition would be the gradient equals to 0. Simple. The gradient equals to 0, but in the Wasserstein sense, and also in the L2 mu star sense. It's mu star almost everywhere. We have seen here, mu star almost everywhere. The sufficient condition with convexity plus 0 belongs to the subgradient. That's a total analog to for the Euclidean setting in the linear space. For constraint optimization problem, it's similar to Lacan multiplier method, but I want to again emphasize the difficulty in the analysis of for constraint or for sufficiency condition due to the positive curvature of the space. Yeah, and that's all today. And here are 5 references I would use. It's highly recommended to, if you are interested in this topic, just to check the first paper. The whole talk is based on the work from Nicolas Zenti, Bolognani, and Dufler in this paper. First of all, the conditions for optimization in Wasserstein space. Yeah, and as I mentioned here, the remedy is the theorem 3.13 in this paper. And that's all I want to talk today, and let questions come.
Okay, thanks.
Yeah.
Thank you.
So I asked all of my questions during the talk. Other questions?
So do you know if they're using this idea of subdifferential? They have developed any kind of subgradient algorithm or something like that in these spaces?
So non-smooth.
Yeah, non-smoothness. If the subdifferential or subgradient is fine, so the function that is non-smooth, anyone non-smooth.
Yeah.
But the analyze for on linear space is much more simpler than on the Wasserstein space, I would say.
Yeah. Do you think? I mean, so there, as you know, we're approaching several different strategies for defining a subdifferential.
Yeah.
One in terms of first getting a hold of a normal cone. But it sounds like from your presentation here, normal cones could be really complicated.
Yeah, because in a nonlinear space, we cannot even define what kind of set is a cone, because it refers to the direction.
Normal bundle.
Yeah, so we can.
The whole analysis.
You talk about no bundle.
The fact that normal directions are cones is actually not important.
Oh.
I don't believe that. So
Okay.
just normal bundles. So that seems like that would be difficult. The other strategy is, this alpha convexity.
Yes, alpha convexity
seems related to proximal or conjugations or against or a proximal like Moreau envelope.
Yeah. Yes.
And so that is the other strategy of maybe trying to define subdifferential
using
the Moreau envelope.
Yes.
From alpha convex measures.
Yes. I think that's probably depend on or based on the fact that the Fischer differential of this envelope is I think 1 divided by lambda times x minus proximal.
Yeah.
Yeah, but I would say we can similarly define the proximal mapping and the envelope mapping on the Wasserstein space. Of course, that's something we can do. But here are two main difficulties here I can see in the first moment. Firstly, as I said, the proximal defined on the Wasserstein space, well, it seeks for the argmin of some functional j plus some constant whatever plus times the square of the distance, for example. But since the whole space is positively curved, it's not uniformly convex. The first difficulty would be it's hard to find or to argue the existence of the minimizer. This would be the first thing.
Okay, so the Wasserstein space is positively curved, but if you restrict yourself to absolutely continuous function, then you got a uniquely geometric space.
Yes.
Positive curvature, but
yes.
you also made the comment somewhere that it's not locally flat.
Not locally.
So maybe that is going to be a really difficult feature, because I've used very strongly the fact that in uniformly convex spaces, they're sort of locally flat.
Yes. And the second difficulty I want to mention would be how to define the spatial differential of the Moreau envelope. Of course, the Moreau envelope is the infimum or the evaluation of this proximity. That will be difficult to derive. But I have seen some papers on the Wasserstein prox, but they are usually used to connect it to some KL divergence. And yes, KL divergence and some flows methods, I would say.
Okay, thank you.
Yeah, yes.
If there are no more questions, okay, thank you everyone for attending the seminar. So just to remind that this is the last section for the semester. We plan to restart on the middle of September. So at the beginning of September, we will send the announcement of the first talk, and probably our idea is to try to have the schedule for the seminar in the next semester. Okay,